Hi everyone, and welcome to another session on practices with gate-based quantum computing 2. Um, we are talking about the QAOA. We already know where does it come from, what is it, what's the definition, what are the steps that it follows, and today um, we're gonna be talking about one example that probably makes it easier for you to um, understand better the QAOA. So in this session today, what we are gonna see is how we get to the mathematical definition of the total Hamiltonian and what does it mean mathematically, but also afterwards when we are gonna try to implement the circuit. Um, how are we going to get from the Hamiltonian to the circuit, and why are we taking those steps? So welcome to today's session. Um, and as always, feel free to ask me if you have any doubt or anything. As my mail is at the beginning of the deck, it will be shared. So just send me a mail and we can go through whatever you want. So let's jump right in. So what is the max cut problem? For that, we need to know, of course, what is a maximum cut. Max cut comes from maximum cut, and that's the partition of the graph's vertices into two complementary sets. Complementary means that if you have the full graph, the vertices that are in one set are not in the other one, but both of them make the total of the vertices. So we want to have a set or a partition of those vertices such that the number of edges between them is as large as possible. That's like the main definition. Um, so when we represent it, as you see in the picture at the left um, of the screen, when we represent it in 2D, in a 2D representation, this can also be applied for 3D representations and all, although it complicates a bit the mathematical expressions. Um, so the thing is that it of course doesn't have to be a straight line between the vertices. Actually, um, in the approach that we are gonna take, we don't need to know what's the shape of the edges. You just you just know that the an edge connects one vertex to another, and that's it. That's all you need to know. Another definition for the maximum cut or max cut problem is the one that is in the second paragraph. If we define V as the set of all the vertices of a graph, um, we can look for the subset S pertaining of part of V of the total of vertices, such that the number of edges between S and T, that is the rest of the vertices that do not correspond to S but they belong to V, is as large as possible. So um, we need to cut this graph in the way that we cut the most edges um, as possible. Um, of course, when we have a representation like this, so geometrical, it's easy to see it like in a visual way. Um, when we get another, if we get 4, it's easy. If we get 8, it's easy. When we get to 1,000, whatever, it's gonna be so much complicated. And the more we grow the number of vertices, the more complicated, of course, is the problem. This is an NP-hard combinatorial optimization problem. And of course, we can try to solve it with the QAOA. So this is one example on how the QAOA can solve hard combinatorial optimization problems. Here, what we have, I mean, if we try to get to the solution of the problem in a visual way, that's what we have in the right of the in the right corner of the slide. Um, Vertices 1, 7, well 1, 3, 5, and 7 would be the ones corresponding, for example, to S, and the vertices 0, 2, 4, and 6 would correspond to the other set, to T. And this here, if you imagine it like a bit rotated and also like a square, you can see that the corners of the square would be, for example, the 0, the 2, the 4, and the 6. And the other ones would get in the middle of the square. If you get something like that, you you would get why this is called the ring of disagrees. Um, this is or the square of disagrees. So this is one like really common set of or graph in the in the maths behind all of this. This is what we are gonna try to solve right now. Afterwards, we will solve it with code. I tried to make it visual so we know from the beginning what the answer is, and we can just focus on how are we solving the problem. So let's jump into the mathematical representation. So to use quantum computing, first of all, we need to know that we there are some gates or some operators that we will use in a quantum computer. Um, those like the Hadamard gate or the rotations, the Pauli matrices, etc. So we want to get some solution that is or some Hamiltonian that is easily translatable to a quantum computer. So we want to express it with those kinds of matrices or operators. Um, if the concept of the problem we can translate it into a mathematical expression, it's because we know how to map the problem to those qubits, or what those qubits would mean in our solution. So in this case, the qubits would be associated for each vertex, and whether or not they are in a set. So the classical problem of partitioning the graph into two sets would be either if the vertex is in the set S, it could be denoted by 0, by the state 0. If the vertex is in the set T, it would be in the state 1. It's as simple as that. You can also define the set S denoted by 1, of course, and the T denoted by 0. The only thing is that they should be the different states. So to construct the Hamiltonian, we will think about this instead of on vertices on edges. Why? Because an edge connects two vertices. And that way we are comparing the values of one vertex to the another vertex. We're not comparing the vertices that are not joined by one edge. So for example, in the previous slide, in this one, we are not gonna compare the 0 and the 5 vertices because they are not joined by one line or by one edge. Only 0 with 1 and 0 with 7, 1 with 2, 2 with 3, 3 with 4, etc. So for each edge of the graph, we want to reward the system. So if we're gonna try to either minimize or maximize, we're gonna go in that direction if the edge crosses the partition between sets S and T. That means that if one vertex is on set S and the other vertex is on T, that's something that we want, because we would be cutting the the graph. If both vertices would pertain to S, for example, they wouldn't be on any frontier between S and T, so they would both be at the same, let's say, side of the division. So we wouldn't get a partition of the edge there. So we have defined that. If, of course, if the edge doesn't cross the partition, if the edge is not divided, both vertices could be in the same set. So we don't want to count this edge. So the contribution for us should be 0. And the other way, we would want to be 1. So this way, we will be maximizing the Hamiltonian if the vertices correspond to different sets. So we also know that the Pauli Z operation has 2 eigenvalues. If you can also make the multiplication between the usual matrix into the Pauli Z matrix. That is a diagonalized matrix with 1 and -1 in the diagonal. You can do it if you need to get to these eigenvalues, but the eigenvalues are the numbers on the diagonal when it's diagonalized, so they are 1 and -1. 1 when the qubit is in the state 0, -1 when the qubit is in the state 1. So for each edge, we can use the product of the Pauli operators Z in the vertex U and Z in the vertex V to get the relative positions of the 2 qubits. What does this mean? So if we define an edge by the multiplication of Z1, ZU, and ZV, we would have a multiplication of the values that we have there. So we have +1 multiplied by -1, +1 multiplied by +1, and all the other combinations. Depending on which state the vertex is, what that means, which set does it belong to, S or T. So if both qubits are in the same state, that means either they are both in the state 0, they belong both to the state S, or they are both in the state 1, they belong both to the set T. The edge does not cross the partition, so the edge is not divided because the vertices correspond to the same set. That would mean that we're multiplying +1 by +1 or -1 by -1. The other case, if Z on U and Z on V are -1, the qubits are in different states. So one is 0 and the other is 1. It doesn't matter if U is 0 or U is 1. The important part is that they are in different states. So if they are in different states, that means that one belongs to the set S and the other one belongs to the set T. That is exactly what we want. Remember, maximum cut. So if we normalize that expression to get a result of 0 when we do not want the state to contribute, and 1 when we want to impact our energy landscape instead of -1 and +1, we'll get to this coast Hamiltonian, summing all of the edges in the graph. So we have the it's summing through UV, so on pairs that can only take values as we said before. So 0, 1, 1, 2, 2, 3 in our case, and we are making this transformation. It's an easy transformation. It's the same as when we are changing from the spin 1 minus 1 to 0, 1. This is a usual transformation. So here, why are we calling this the cost Hamiltonian? Because this is the Hamiltonian that will solve our problem. Why does it solve our problem? Because we've modeled it like that. So this is the Hamiltonian. If you remember the previous classes that we were talking about, mixer Hamiltonian, cost Hamiltonian, and all the adiabatic process. This is the Hamiltonian where we will end our adiabatic evolution. If we remember that this is not a real adiabatic evolution because this is like an approximate approach. So we are Lagerizing this, but you do have a similar connection. So the coast Hamiltonian would be the Hamiltonian where the system would end the evolution, and if we do it right, the system would end it in the ground state of the coast Hamiltonian. So we would solve our equation. So we got to the coast Hamiltonian. Let's see how can we get to the total Hamiltonian. So if we sum the usual mixture Hamiltonian, that is that one, we get the total Hamiltonian. Why this is the mixer Hamiltonian? So it's usually defined like that in many other algorithms that use a similar approach. We use X matrices because the mixer Hamiltonian, what is doing in this process is trying to not get stuck in a local minimum. So if we're trying to, you can imagine the landscape of our energy landscape, okay, that is has its local minima and has the ground state that is the most minimal one of them. So we don't want to get stuck on a local minima and understanding that as a solution when probably it's a solution but it's not the best one. This mixer Hamiltonian is called mixer because it can get us out of that simply by changing one of the qubits. It can mix a bit the status so we can skip that little local minima and try to go to other ones. That's the main job of this Hamiltonian here. That's the main concept that this term has here. So then we would have two Hamiltonians. The sum of two Hamiltonians would model our whole problem. The first one, the mixer Hamiltonian, the one that gets us out of the local minima, and the other one that gets the general landscape and gets it's encoding the problem that we are trying to solve. So here we can see that we have X matrices, we have multiplication of Z matrices. So how are we gonna get this into a circuit? Afterwards, you will see how we can code it in using Qiskit. You will see it for this number of nodes or vertices for this exact graph. But I want you to think a bit when you see a Hamiltonian, how can you translate it to a circuit before implementing it in IBM or in whatever other technology vendor you would use? We have X gates, we have Z gate combination, so probably controlled. And we will start, of course, by uh, make the superposition of all these states. So our circuit will be, initially, we can think about it, uh, building it from Hadamard gates, always to initialize the system. We will have controlled Z gates because we have that multiplication of Z matrices that it's kind of a controlled Z gate, right? Um, um, and we will have X rotations because we have the X matrix there. The control Z gates will, as we know, both of the Hamiltonians um, are going to be parameterized in unitary operators. Those operators will have each of them a specific angle. That angle is the rotation along z or the x axis, and that angle will be adjusted. So the control z gates will depend on gamma, that is the parameter that we defined before in the previous session. The x rotations will depend on the parameter beta, that will be the angle of the rotation. The coast Hamiltonian that you have there will be the operator that has again the um, that will evolve when optimizing one parameter, the parameter gamma, and the other one will evolve when optimizing the parameter beta. You have there an example of how a QAOA is implemented without knowing what the coast Hamiltonian and the mixer Hamiltonian, what form will they take. So this serves for other Hamiltonians, other forms of Hamiltonians. But first, you initialize the system with all those Hadamard gates applied to every state that we have, and afterwards you start layerizing the process. First, you apply one unitary transformation, then you apply the other one, and that goes on and on and on and on. In between those layers, we will have an optimization of those parameters. So layer 1 won't be the same transformation as layer 2 because both beta and gamma will change. We will define when we make the circuit, when we start coding and programming, we will decide if we when do we want to stop to optimize those parameters? When do we think that that would be enough for us to get the optimal solution? If we did infinite layers, we will have the continuous evolution. We will go to the best solution, but this is not the case. We are layerizing it, so we have n layers. We can define them, and then afterwards we will measure everything. So as always, all the computation is made on the quantum computer or the simulator, but the optimization is not done with a quantum computer. The optimization is done with classical computations. This is a mixture of classical and quantum computing, and we can get to some approximate solution this way, in a simple way. As you've seen, also the maths are really simple, and we can solve really complex problems. As always, in all the sessions, if you have any doubt, just reach me out. I'll see you in the next session. We will code together to implement this exact example using QCT. you will also have the code shared, so you can go through it, either building it with me, or you can also go through it with it like done, like completed. So yeah, thank you all for watching. See you in the next session.